You can gather a lot of information about the motion of an object by viewing graphs of motion. There are many different types of graphs for motion or moving objects. The first one that we're going to look at today is called a position time graph. Position time graphs have position on the y-axis and time on the x-axis. So below, we have an example of a position time graph for a rolling ball. If you take a look at this graph, you'll notice that it's a straight line. That indicates that there's a linear relationship between the position and time. When mathematicians see a linear relationship, one of the pieces of information that they can collect is the slope or steepness of this line. Slope is defined as rise over run. In this case, delta y over delta x. Now we said that the y-axis is labeled position, so that would be delta d over delta t, the change in position over the elapsed time, or delta t. We can expand this to mean position number 2 minus position number 1 divided by t2 minus t1. This should look familiar to you. This is the equation for velocity that we learned at the beginning of section 1.2. In fact, if you find the slope of a position time graph, you will determine the velocity of the object. We're going to place that statement behind the bars of memorization, and we'll come to know that this is an important statement, an important piece of information we gather from a position time graph. So let's find the slope of this graph. We're going to use these 2 points, 0, 0, and 40 meters east and 10 seconds. So the slope of this line would be 40 meters east minus 0 over 10 seconds minus 0. Punch this into your calculator. You end up with 40 divided by 10. That's 4 meters per second east. Notice 40 is one significant digit and 10 is one significant digit. So 4 meters per second east is one significant digit. The velocity of this object is 4 meters per second east. So this object is moving at a constant speed of 4 meters per second in a straight line. We can say that the object is demonstrating uniform motion. Now that's not the only shape of a position time graph or the only type of motion that we can plot on a position time graph. We're going to look at several examples. The first example is the basketball shown in this first diagram. If you notice, the basketball is stationary and it's located some distance to the east of this person. So we'll say that the object is at rest at a position that is east of the person. So what would that look like on a position time graph? Well, if you imagine the object is holding its position over the entire interval of time. So the object's position remains the same over time, and it ends up looking like a horizontal line. Note that horizontal lines have no slope. So we said that slope is equivalent to velocity. If there is no slope, then there is no velocity, and this object is at rest. In the next diagram, the basketball is still at rest. This time, it's at a position west of the person. The position time graph is expressed in the direction east. So how do we indicate that the object is traveling, or is at rest rather, but at a position west? To change east into west, we would have to change the sign. So this would be a similar graph, a horizontal line because there's no slope, the object is at rest, but this time it would be below the x-axis. Below the x-axis, the y values are negative, and negative values indicate the west direction. So a position time graph for an object at rest at a position west of the person would look like a horizontal line below the x-axis. Let's look at the next moving object. Here we have a runner that is running at a constant speed in a straight line. That means that the object has a constant velocity in the east direction. So how do we indicate constant velocity in an east direction? Well, we've seen this in the example above. Constant velocity on a position time graph is a straight line with slope, and the value of the slope gives us the magnitude and the direction of the velocity. In this next example, imagine that the bicyclist is traveling at a greater velocity than the runner. Still traveling in the east direction, this time we want to show that it has a greater velocity. So what does greater velocity look like on a position time graph? Greater velocity means greater speed in a straight line. So we show a straight line with a greater slope. Since slope indicates velocity, the steeper the slope, the greater the velocity. In the example below, we have the same speed in a straight line, this time traveling in the negative or west direction. So how do we show negative velocity or velocity in the negative direction? Well, this would be a straight line with slope, but this time it's a downward sloping line. Next, let's look at a position time graph for non-uniform motion. Here we have a line that is not a horizontal line and it's not a straight line, it's an upward curving line. So if we look at the steepness of this curve, we notice that the steepness is changing over time. That tells us that the object's velocity over the interval is increasing as time goes on. It's getting steeper as time goes on. So what if we wanted to know the velocity of the object at a particular moment in time? For example, what if I wanted to know the velocity of the object, the instantaneous velocity of the object at 2 seconds? Well, let's take a look at this graph at the point t equals 2 seconds. If you wanted to determine the velocity of this object at the particular instant 2 seconds, what you would need to determine is the slope of the line at 2 seconds. So behind the bars of memorization, we write this important statement. The instantaneous velocity is equal to the slope of a tangent line at a specific point. And what is a tangent line? Well, the tangent line is a concept in mathematics. It's a line that touches the curve at only one particular point. And we want to draw a tangent line such that it touches the curve exactly at t equals 2.0 seconds. just like this. And if you look closely, this line is touching the curve at exactly t equals 2.0 seconds. If you could determine how steep this line I just drew is, it would tell you the velocity of the object at 2 seconds. It would give you the instantaneous velocity at 2 seconds. Let's do that. So instantaneous velocity is equal to the slope of the tangent line. So the velocity will be equal to d2 minus d1 we'll look at these 2 points here. That's position 2 and position 1, occurring at t equals 3 seconds and t equals 1 second. Let's look at the corresponding position values. We have 8 meters east and 0. So the velocity will equal the slope of this tangent. That's d2 minus d1 over t2 minus t1. That's 8 meters east minus 0 over 3 seconds minus 1 second. If you simplify this, you end up with 4.0 meters per second east. Therefore, the instantaneous velocity of this object at t equals 2 seconds is 4.0 meters per second east. Now, since the object's velocity is changing over the entire interval, an important piece of information would be to report the average velocity over the interval. And that's what the second sample problem asks us. It's asking us to determine the average velocity over the interval 0 to 4 seconds. And this is how we find the average velocity. The average velocity between any 2 points on a position time graph is equal to the slope of the line joining the 2 points. So we're going to do just that. We're going to draw a line that joins the points t equals 0 seconds and t equals 4.0 seconds. So we'll draw a straight line joining these 2 points. And if we find the slope of this line we just drew, we will find the average velocity over the interval 0 to 4 seconds. Let's go ahead and do that. Average velocity is equal to the slope of a line joining 2 points on a position time graph. So it's equal to position 2 minus position 1 over t2 minus t1. That's 16.0 meters east minus 0 over 4.0 seconds minus 0. The 2 significant digits, it's 4.0 meters per second east. So the average velocity over the interval 0 to 4 seconds is 4.0 meters per second east. In the example above, we found the instantaneous velocity at 2 seconds and it was 4.0 meters per second east. And the average velocity over the interval 0 to 4 seconds was also 4.0 meters per second east. Is this a coincidence? Is there a relationship between the interval 0 to 4 seconds and the point t equals 2 seconds? Well, t equals 2 seconds is the midpoint of the interval 0 to 4 seconds. So, is that a coincidence, or does the average velocity over an interval equal the instantaneous velocity at the midpoint of the interval? Well, it is a general rule. Take a look at the line joining 0 to 4 seconds. If you compare it to the line we drew at t equals 2.0 seconds, you'll notice that they are parallel. It means they have the same steepness or slope. If they have the same steepness or slope, then we can say that they have the same velocity. So the average velocity over the interval 0 to 4 is equivalent to the instantaneous velocity at the midpoint of that interval t equals 2.0 seconds. In fact, this is a general rule for all motion with uniform acceleration. Let's write this rule down. This rule states, the instantaneous velocity at a midpoint of an interval is equal to the average velocity over the entire interval. And we'll write this statement behind the bars of memorization. And this rule becomes important because sometimes drawing a tangent line is really tricky. It's tough to draw a line that touches the curve at exactly one point. And once you do, it's kind of inaccurate to draw or to calculate the slope of that line. So instead of finding the instantaneous velocity using a tangent line, you can choose an interval such that its midpoint is that particular instant in time. And you can find the average velocity over an interval instead of finding the instantaneous velocity at the midpoint of the interval. This is a really helpful tool. Now let's look at the shape of some other graphs. Let's look at the graphs for objects that are accelerating. In this first example, we have a skier that is speeding up in the east direction as he's moving downhill. So the object has increasing velocity. Since velocity is equal to slope, we have to show an increasing slope over time. And the graph looks like this. It's an upward curving graph, and if you notice, the steepness of this line increases as time goes on. In the second example, the object is speeding up, this time in the west direction. So we mentioned that west is negative east. So this graph would be a graph for increasing velocity in the west direction and would occur below the x-axis, because below the x-axis the y values are negative, and negative east means west. So this graph would start off not very steep and then end up being steeper over time and would look like this, a downward curving line. Let's take a look at the next example. Here we have a bicyclist that is approaching a hill. As he reaches the hill, he coasts up the hill. So he stops pedaling, and as you would imagine, his speed decreases over time. So we want to show a position time graph for slowing down in the east direction. That means decreasing velocity. So this object's velocity starts off very steep and then ends up not so steep. So it would be a curved line that looks like this. In the last example, you can actually predict the shape of the curve based on the patterns that you've seen. We want to show what a position time graph would look like for an object slowing down in the west direction. Again, decreasing velocity in the west direction. Let's try to look for a pattern in what we've drawn so far. Let's take a look at the first two examples. If you notice, they look like they are reflections in the x-axis. Well, the same is true of the last two examples. If the first one looks like this, then the second one would be a reflection in the x-axis. So it would be a downward curving line that looks like this. Starts off steep and then ends up less steep below the x-axis, indicating that the object is slowing down in the west direction. So you'll be able to tell a lot about the motion of the object just by looking at the shape of the curve, and over time you'll be able to interpret many different shapes on a position time graph. Now try the homework questions on page 20, numbers 4 and 6 through 8. Good luck.